Hi everyone, I'd like to introduce you to my first posting of a LEGO technical mock, a LEGO clock powered by pool balls. Yes, you've heard it here first, a clock that is powered by pool balls. This is not one of those clocks that displays the time using a multiple rack of balls. That has been done before, and you can already check the videos on YouTube. This is a clock that runs off the potential energy stored in a pile of pool balls. Why, you may well ask. When I was much younger, I saw in a jeweller's window and craved to buy a novelty clock that was powered by ball bearings. It was beautifully built and designed to be a talking point as well as a timepiece. The balls ran along a winding rail system, and their potential energy was extracted by letting them fall slowly through a mechanism until they exited the clock at the bottom. The operator wound the clock by the simple process of putting the balls that came out at the bottom back in at the top. And that simple, visually attractive idea has stuck with me through the years, and during the 2020 lockdown I decided it might make a fun LEGO Technic build project. Building your own clock in LEGO is always a challenge, and I thought that powering it using pool balls was just the kind of futile and pointless activity that captures the spirit of these lockdown times. Why did I use pool balls rather than ball bearings? Well, because I had old pool balls, and large ball bearings are shockingly expensive. Even buying a budget set of new pool balls would have been cheaper than buying large quality steel ball bearings. Pool balls are also a size that integrate well with the LEGO Technic grid and are heavy enough to generate plenty of clock power, and plus they make that lovely chinking sound as they fall out of the clock. The standard size pool ball will happily roll with stability on a LEGO bar stock spaced apart by 5 studs. Not only that, but it will neatly pass through bars that are spaced apart by 7 studs. These are convenient numbers for the Technic constructor, as it allows an easy way to build towers and ramps using the basic LEGO rectangular frames and bars to transport the balls safely. While on the track, a ball will pass under a bar 6 studs above the rail. However, on a flat surface, the ball will only pass under a rail 7 studs high. To capture the movement of the ball bearings under gravity, you need to be able to transfer their motion into a LEGO gear rotation. And there are many ways to do this, but my designs focused on using a caterpillar track solution. If you have the track in a linear transport arrangement, you can space ball blockers apart by 4 tracks, and the balls will sit nicely in line on the track. I did start by making a lift or elevator style mechanism, as you can see in this photo. In this design, the balls fell slowly down the lift shaft and the track rotated a wheel to harvest the motion. The inherent frictions of the lift mechanism under the weight of the multiple pool balls, however, meant it wasn't very efficient, and I soon moved on to the approach of the Ferris wheel. If you wrap the track around the turntable, it will fit exactly, and you can use a spacing of 3 tracks between blockers to make a continuous loop. The balls fit into the narrower gap because its curved surface of the wheel turns out all the blocker pieces and makes more space. 15 balls can be wrapped around the full circumference of the resulting Ferris wheel. So let's go through the basics of what you're seeing here. At the top you can see the roll of pool balls that are queued up to power the clock. At the bottom are pool balls that have done their work and have been ejected with their potential energy used. The balls pass round one half of the Ferris wheel, constructed using Technic turntable parts, around which is wrapped caterpillar track fitted with ball blockers. The balls, held back by the blockers, cause the turntable to rotate under gravity, and that motion is picked up by a cog meshing with the turntable rail. There is more to the Ferris wheel design than simply wrapping track around it. The quadrant part of the turntables flex, and the weight of the pool balls cause the wheels to want to lose its shape. If that happens, the cog that meshes with the wheel will start to skip under load as the distortion opens up the gear teeth. The wheel therefore needs substantial bracing to ensure that it resists distortion under the weight of the balls. Wrapped around the Ferris wheel is a ball guide that stops the balls falling out of the wheel. The design of this was quite tricky, as the rails system needed to follow a circle in space just larger than the sweep of the balls around the wheel. This involved creating some unusual angles in LEGO rails. The current solution you see works very well and has never lost a ball. The bracing struts you see are there to stop the weight of the balls on the wheel from pushing the rail and wheel apart. The track itself is continuous inside the guide, and as the balls slowly rotate, they transfer their weight from the ball blockers on the wheel to the rail system in the ball guide. At the bottom, the last part of the rail system gradually moves away from the wheel, opening up the spacing until the balls drop free and roll into the spent tray. It is important that the wheel does not hold on to the balls for too long, as they eventually become a dead weight that needs to be pushed out, wasting more energy than they provide. A gear train system then increases the rate of rotation many times before ending at an escapement mechanism where the clock regulates the release of the motion. The easiest way to see how the ball mechanism operates is to stop the clock escapement from holding back the ball power and let it run freely. Without the timing regulation of the pendulum, the escapement wheel spins madly and the ball races through the track. Reapply the pendulum and all that potential energy is held back again for the clock to run on. The first stage of the gearing is thus a massive gearing up to power the escapement wheel. In this build, there are 4 stages of gearing, each of 3:1 ratio, plus the initial gear reduction from the Ferris wheel of 11.66, making a total gear ratio of 945:1. If it sounds a lot, then it is still not enough in truth. This clock will only run for about an hour on a full set of balls, and so this is more of a demonstrator of concept than a realistic timepiece. One aim of a better design is to increase this gear ratio by a power of 30, so that a set of balls will last 36 hours. The next stage of the clock is the escapement, and the accompanying pendulum to regulate the release of all that ball energy. The escapement wheel uses 3-star point part commonly used for making propeller bays in Technic sets. They are beefed up with rod connectors, and the escapement latches are fitted to the pendulum itself. This mechanism started out as a complicated set of rods and leaders are used to adjust the striking point of the lever with the wheel. After much fine-tuning, I discovered that the ideal striking point sat right on the Lego grid, and it meant I could fit this extremely simple pair of bars instead. Once set in motion, it is proving extremely reliable, so long as the motive power of the balls is sufficient. The pendulum itself swings on a single Lego axle rod that lies in a shallow V. A knife edge would have been better, but I lacked the necessary Lego parts, and this worked for this stage of development. When I checked the rates of rotation of the intermediate shafts, I had a stroke of luck in that one wheel rotated in 29 seconds right off the bat. So with the addition of a pendulum height adjustment, I was able to fine-tune the rate of rotation by 4 seconds either side of 30, enough to allow calibration of the finished clock. The next stage of the design was to gear down that key 30-second rotating wheel so that it went round once every hour, and this provided the rotation of the minute hand of the clock, and so a reduction of 120:1 was needed. This was provided by an initial 2:1 reduction straight off the escapement, meaning these 2 cogs here rotate once per minute. Then there is a 5:1 reduction, followed by a 3:1, and then a further 2 2:1s, and that makes 60, so the end shaft rotates once per hour and needs to correct directly to the clock hour hand. Moving on to the clock itself then, as you can see, it's also made using the frame of a Lego turntable. This provides suitable hanging points for the 12 points of the clock markings on a circular face. I was particularly keen to ensure that the minute and hour hands rotated on the same axes, and as many others have discovered, this rather limits your Technic options. I also wanted to hide the gears from anyone that simply wanted to read the time, and so I filled in the hole in the turntable and just left enough space to get the hand mechanism to poke through. To show how the clock mechanism works, I've removed the clock from the frame. The problem to solve is to take the minute hands that goes up the centre shaft and to divide the rotation by 12 for the hours before putting that rotation back onto the same axis as the minute hand. In my design, I used the older style Lego differential housing for the hour hand rotation. It allows a Lego axle to pass straight through it for the minute hand, but also has the gear so that it can be independently rotated around that shaft. This housing can be married with a sister cog to create a 2-to-1 gear reduction. Normally, the sister gear meshes at 90 degrees, but in my design it lies in the same plane. To complete the 12-to-1 reduction, therefore, needs another 3-to-1 gearing and then a final 2-to-1. The trick was to organise these gears so that the final rotation is back onto the same axis as the minute hand which it must connect to. I'm quite pleased with this part of the design. My solution was compact by LEGO standards and the gears couldn't be much tighter integrated. Another bonus was that the design needed an extra 1-to-1 gear to get the rotation of the hands to both go in the same direction. But that allowed me to have 2 shafts where I could bring in the drive to the clock hands. As these cogs counter-rotate, the design means you can connect to whichever shaft matches the rotation of your incoming hour wheel. So the remaining task was just to unite the clock hand to the hour wheel. Because of the spread out nature of the clock necessitated by the size of the ball racks, it was not possible to sight the clock very near to the hour wheel. I resorted to using a 1-to-1 shaft drive to connect them, as that is able to fix any and all mismatches. This is perhaps one of the most compromised bits of the design, and it must introduce some unnecessary backlash to the minute hand rotation. A better design would manage the positioning of the key components more thoughtfully to avoid unnecessary gears and long flexible shafts. Well, that's it for an introduction to the pool ball powered clock. I'd be interested to hear any reactions from the LEGO community, particularly as to how I might solve some of the outstanding problems or to simply improve and develop the design. No need to comment on the utter pointlessness of this enterprise. I am already proud enough. I was well aware of the limitations that LEGO would create, even as I did it. It was just a fun design, done for the hell of it, and needed to be viewed with that perspective. It gives me something to show and explain to my bemused grandchildren, who are all LEGO mad. I would love to improve the design and make it more practical as a clock that can run for up to 36 hours on a single loading of pool balls. Areas I will therefore be looking at then are a more efficient escapement with less rotation per tick, a higher gear reduction between the Ferris wheel and the escapement that doesn't suffer stiction, and a better overall layout to compact the clock frame while still handling the same or more balls. On that note, I await any comments and thank you for your patience.